Today we're going to be looking at section 4.3 and 4.4. So these theorems that we're going to be writing down today for your notes are triangle congruency theorems. So they tell us whether or not two triangles can be proved congruent without listing all 6 things, like all 3 pairs of corresponding angles being congruent and all 3 corresponding sides being shown as congruent. So with these things, usually there's just 3 things that we need to show are congruent instead of all 6. So the first one is side, 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 or SSS. It says that if we've got the 3 sides in the triangles being congruent to each other, then we know that the triangles need to be congruent. And so this is the way I defined it. If you want more technical terms, you could look up how the book defines it in section 4.3. So basically, it's just saying if we've got like triangle ABC and triangle LMN, AB we show is congruent to LM, BC is congruent to MN, and CA is congruent to NL. Like we have 3 pairs of corresponding congruent sides, we can go ahead and say that the triangles are then congruent. And you can have the sub pause this if you need more time to write that down. I'm going to go ahead and move on to the next theorem, which is the angle side angle theorem, or ASA. So this says if one triangle's 2 angles in the included side are congruent to the other triangles, 2 angles in included side, then they're congruent. Now, the important thing to realize with this theorem is that when we're talking about 2 angles in a side, the side has to be in between the 2 angles. Like if you were to start at the leftmost angle and then go clockwise, those would all be in the ASA, or angle side angle order. So you'd come across an angle, a side, and then an angle. Same thing with the other triangle, an angle, a side, and then the angle. That's what we mean by included side. The side is right between the 2 angles. So I couldn't use the side DF and GI for the congruent side because that would be angle, angle, side, and that would not be this particular theorem. Okay, for this theorem to work, the side has to be right between the 2 angles. It's got to be the side that the 2 angles share. Okay. Alright, again, you can ask for this video to be paused as you write that down. I believe this theorem might be in section 4.4 if you want the book's definition. Alright, so let's look at side angle side. Just as its name implies, we've got 2 sides being congruent to each other and the included angle. So that means just like the one previous where the side had to be right in between the 2 angles, on this one the angle needs to be right in between the 2 sides. Okay? The angle that we are using needs to be the one that is made up out of the 2 sides. Okay? So see how angle JKL, one of its sides is KJ and the other side is KL? Okay, and those are the 2 sides that are included as being marked as congruent. Same thing for angle RQP. Its sides are QR and QP. Those have to be the 2 sides that are shown as being congruent, otherwise it's not SAS, or side angle side. And then the last, well, not the last one, but the 4th one is angle angle side, which we mentioned for a second up in one of the previous proofs, or theorems, that says if one triangle's 2 angles and a non-included side are congruent to another triangle's corresponding 2 angles and non-included side, then the triangles are congruent. So in this case, if we look at the triangles STU and XYZ, we've got angle S and U being shown as congruent to X and Z, and then we've got this extra side. It is not the included side, meaning it's not the one between S and U. Okay, so it is not the one they have in common. So we could have either marked TU and YZ as being congruent, or if we were still using AAS but not side TU and YZ, we could also mark ST and XY as being congruent, and still use angles SU and XZ. Okay, because ST and XY are not the side that those 2 congruent pairs of angles share in between each other. Okay, so far we've got SSS, ASA, SAS, AAS, okay, and there's one more combination of sides and angles that we need to look at, and that is side-side angle. Now, you might be thinking, yeah, that makes sense to have a side-side angle or SSA theorem. However, if you actually try to use this one, it is not a real theorem. Okay, and I like to remember that this one isn't a real theorem because if we were to write out the abbreviation SSA, it would spell a bad word backwards. Okay, so that is not an actual theorem. It doesn't work. Let me see if I can show you why. So let's say we've got something like this where we've got a side, and an angle. This is why it wouldn't work. We could also have this same angle being congruent. This side is congruent to the other two tick-marked side. However, if I rotate this other side and still make it, well, that wasn't a very good drawing, but if I made it hinge out a little bit, there is a possible case where the two sides are congruent and this angle is the same, but those are not the same triangles. Like, you can clearly see that this is an obtuse angle right here, and this is maybe a right angle or a slightly smaller obtuse angle. So there are cases where you've got a side, and angle being congruent to each other, but they are definitely not congruent triangles. Okay, they're not the same. Alright, so that's why SSA is not a theorem. However, there is a special type of SSA that is a theorem, and we actually call it something else. We call it the hypotenuse leg theorem, or HL. Now, the reason this one works is because it's always dealing with right triangles. Okay, if they're not right triangles, then we can't use it. It's not an actual theorem. We can't prove that they're congruent. So hypotenuse leg theorem says if a right triangle's hypotenuse and leg are congruent to another right triangle's corresponding hypotenuse and leg, then the two triangles are congruent. So you want to remember that a hypotenuse on a triangle is always the longest side, or the side that is across from the right angle. So if we look at triangle Matt and Ben, triangle side AT is the hypotenuse for Matt, and side EN is the hypotenuse for Ben, because those sides are the ones that are across from the right angles. They are the longest sides in the triangles. Okay, so if you're looking at two right triangles and you've got their hypotenuses being congruent to each other, and then they've got another pair of legs congruent to each other, then you can say they're congruent. And for a right triangle, the legs are just the non-hypotenuse sides. So MT and BN are legs. We also could have used MA and BE for legs. That would have been fine as well. Again, so when you look at the picture, it looks like we've got SSA for side-side angle. However, we don't call it that. We call it HL as a hypotenuse and a leg because these are specific kinds of triangles. They're right triangles, and that's the only case in which this works. Okay, let's look at one more theorem. This is the base angles theorem. You're going to see this on one of the proofs on your worksheet for the homework. That's why I included it here with the triangle congruency theorems. This is just saying that a triangle's base angles, or two bottom angles, are going to be congruent if and only if the opposite sides are congruent. Now, if you remember back to chapter 2 when we looked at like the biconditional statements, if and only if means that this could go either way. We could say if a triangle's base angles are congruent, then the opposite sides are congruent. We could also say that if a triangle's opposite sides are congruent, then, or if a triangle's two sides are congruent, then the triangle's opposite angles are congruent. So we could go either way. So here's some pictures of that. So, for example, if in triangle ABC we see that A and C, those two angles are congruent, then we can say their sides that are opposite to those angles are congruent. So the side opposite to angle C would be side AB. The side opposite to angle A would be side BC. So if the angles are congruent, the opposite sides are congruent. Vice versa down here, we're given the same triangle, however this time we're just told that AB and BC are congruent sides. So given this theorem, we could also say that, oh, well, the angles opposite to those sides must also be congruent as well. So A would be congruent to C. Okay, again, you can pause the video if you need to write that down. This theorem, it is in either 4.3, 4, or 5 in your book. So if you need to find that in the book because you don't like the way this is written, that's fine. Here's an example of a lot of the types of things you'll see on your worksheet on the front page. So we want to say if the triangles are congruent, and if so, by what theorem. So first of all, we have to identify what two triangles we're talking about. So if we look at this first image, there are two triangles in here. It's not just a four-sided figure. So the first triangle is in this like upper left-hand region. It's where I'm coloring it blue. And then the second triangle is in the lower right-hand region, in the red section. Okay, so to show that those two triangles are congruent, we need to have some things. We need to show that either all three pairs of sides are congruent. We need to show that two sides and the included angles congruent, or two angles and the included sides congruent, or just two pairs of angles and then a side, or we need to show that they're right triangles and they have a hypotenuse and a leg being congruent. Alright, so there's some clues here that we're going to use. If you remember from earlier, these arrows on these sides means that those two line segments are actually parallel. So if they're parallel, that usually hints at congruent angles, and I'll tell you why. If we extend these sides and just kind of like envision them as our railroad tracks, and then extend this diagonal like it's a tie on the railroad, we just created two, there's the two parallel lines, and then that long railroad tie is our transversal. So from the end of chapter 2, we learned that given two parallel lines in a transversal, there are all types of angles that are congruent. So like the alternate interior angles are congruent, the alternate exterior angles are congruent, corresponding angles are congruent, and the consecutive interior angles are supplementary, meaning they add up to 180. So in this case, we're looking for congruent angles, so we can kind of forget about the consecutive interior. We don't care about that right now. So let's see, given those parallel lines, I'm going to look for angles inside the triangles that are also have some sort of relationship with each other with that transversal. So if you look at this figure, we've got an angle right here and an angle right here that are both in those triangles, and those are alternate interior angles. So we know that those two are congruent. Okay? Alright, so there's a pair of angles that we know are congruent. Let me just erase these extra lines so we can look at our original picture. Okay, so we've got one pair of angles, we have one pair of sides, those are the black tick marks, and then we also have one more pair of sides. Okay, they're not marked anywhere, they're the ones that the blue triangle and the red triangle share. So if we look at the blue triangle's lower right side, this one that I'm marking with two tick marks, that's actually the same side as the red triangle's upper left-hand side. So since they share that side, we know they must be congruent. That's using the reflexive property, if you wanted to know the actual property name, back from chapter 2 that says that something is equal to itself. So here, if we look at it, we've got a side here in the blue triangle, an angle, and then another side. And the angle is actually the one that is made up of those two sides. And if we look at the red triangle, that angle is also made up of the two given sides. So we would say, yeah, these two triangles are congruent by the side angle side theorem, or SAS. So A would be, yep, by SAS. If we look at B, again, parallel lines tell us that we're probably going to have some congruent alternate interior angles. So actually there's a couple we could mark. So there's this pair of alternate interior angles because of the transversal that goes from the lower left hand to the upper right hand. corner. And then there's also these pairs of alternate interior angles because of this transversal. Now, because we have one given pair of sides, we can see that we have two congruent triangles by angle, angle, side. However, there's more than one right answer to this one, because if we look at when two lines intersect, the angles that are in the opposite spots are called vertical angles, and those are also congruent. So we could mark those as being a third pair of congruent angles. So on this one, we could either use angle, angle, side. Oops. So we could write angle, angle, side. Or if we use the vertical angles and one of the alternate interior angles instead, we could use angle, side, angle. Because if we look at the 2 arc and the 3 arced angles, the side is the one that those two angles share. So that could be another one, is angle, side, angle. You could also use AAS again by using the 1 arc, the 3 arcs, and then the side. So on this one there's two different answers you could have. Both of them, however, lead to us saying, yep, those two triangles are congruent. Alright, let's look at this one. So this one, we've got a pair of sides being marked as congruent. We also know that these are both right angles, because if this is a right angle and this is a straight line, that means this also must be a right angle. So there is a pair of congruent angles. So we've got a pair of sides, a pair of angles. We just need either another pair of angles or a pair of sides. Well, we've got a pair of sides that comes from that reflexive property again, because they both share that middle kind of height line. So that would be the second pair of sides. So if we look at the left triangle compared to the right triangle, those are congruent by two sides and an angle. We know there is no SSA, there is an SAS, and yep, the angle we're looking at is the one that is created from the two sides that are marked as being congruent. So this one would be yes by side, angle, side. Alright, let's look at D. So again, we've got two triangles that share a side. So that's two sides and an angle, because they're both right angles. However, those are, if we look at the order, those are side, side, angle, because the angle is not in between the two given sides. And we don't have a side-side angle, so you might be tempted to say, oh, this is no. However, since these are right angles, those are both right triangles, and since the longest side in both triangle is the one they share, so the one of the pairs of sides that are congruent, we can actually say yes on this one by the HL theorem, or hypotenuse leg theorem. Alright, let's look at the next one. So we've got two pairs of sides, and then an angle. So since the angle is not inside the two sides, or the angle is not made up by the two given congruent pairs of sides, we know that it's not side, angle, side, so that would leave SAS. So that means it's either not possible, or this would be HL. However, we can only use HL on right triangles, so these are not right triangles, so this one is actually no. We can't prove that those two triangles are congruent. Okay, last one. We have got two triangles. They share a common side, so we can mark that one as being a third pair of congruent sides. Oh, and when we've got three pairs of congruent sides, we can just say yes by the side, side, side theorem.